Okay, we're in chapter 11 now, and we're going to cover sections 1, 2, and 3. I'm just going to make, for today, 1 or 2 videos on the basic notation, definitions, things like that we'll need to cover the sequences and series that we're going to go over. And then I'll make videos on specific sequences and series using all of those definitions and notation. But I figure we should at least have one video where I go over all the basic definitions and stuff you need to be able to solve problems. So first off, we're going to look at sequences. We all know what a sequence is. It's a bunch of objects kind of put in a certain order, first, second, third, sequential order. As far as the mathematical definition goes for a sequence, it's just a function whose domain is the positive integers. And I would point out, there's actually, your book defines 2 different types of sequences, finite and infinite. Essentially, most of the sequences we look at will be infinite. Positive integers are infinite, so that makes sense for a domain. Sometimes we can restrict ourselves to a finite sequence, maybe only 100 terms of a sequence, or only 1,000 terms of a sequence. In that case, the domain would just be the positive integers up to a given number for however many terms we wanted. That doesn't really matter. But essentially the idea is we have a sequence, say we have this sequence. 1, 4, 9, 16, 25, and so on. You guys can all tell that's a sequence of perfect squares. 1 squared, 2 squared, 3 squared, and so on. This is actually the range of the function. Those are the values the sequence gives me. The domain would be 1, 2, 3, 4, 5. This is the first term, the second term, the third term. So my domain is the terms of the sequence. And then the range is the actual values for a given term. If we were to graph this, well, the first term at 1 we would get 1, at 2 we would get 4, at 3 we would get 9, at 4 we would get 16. At 5, I'm going to run out of room. At 5, we would get 25. And it looks like that. And there is one important point here. That is the graph of my function. It's discrete points, each point of the sequence. Ultimately, when you get to, say, Calc 2, when you start messing around with this, you actually need to sometimes connect these dots, connect the points, and form a continuous function. That would just be the parabola, the square function, obviously. But for right now, that's not what we're doing, and that is not what the sequence is. This is not a parabola. This does not define a parabola. It defines certain points that if we then wanted to connect those points, we could get a parabola out of, but we're not doing that. We have a discrete function, discrete points. Okay. As far as it goes, sure. This is the first term, the second term, the third term, the fourth term. If we want, we could write this as a function, 1, 1, 2, 4, 3, 9, ordered pairs like that. Generally, when we write sequences, we will write something like this. Maybe for this one, a sub 1 is 1, a sub 2 is 4, a sub 3 is 9, and so on. In general, a sub n would be n squared. You can use any letters you want. By tradition, we use A first. If you have a second sequence, which a lot of times we will, we'll use B. A third sequence would be C, and so on. And the subscript just tells you what term you're on. A sub 1 means the first term, A sub 3 means the third term, and so on and so forth. And you can see my function, 1, 1, 2, 4, 3, 9, and so on. A lot of times we want to be able to list out a general term for our sequence, in which case it's really no different than a function. You need to find the function or find the rule. Here it's clearly squaring whatever number we plug in. So then for any sub n, 7, 12, 37, whatever, you just square it. So then the general term a sub n is n squared. Whatever n is, just square it and you get the value of the function there. And we're going to be messing around a lot with finding these functions and finding these general terms here and seeing what we can do with them. So you want to kind of get used to it. There are other ways to write sequences. There's what's called an explicit form. We're going to look more at that in the next few sections. Some explicit forms that we will need, but we can also use what's called a recursive form. And essentially the idea is, well, I could say something like this. A sub 1 equals 4, A sub n equals 2 times A sub n minus 1 plus 1. And essentially, I give you one term of the sequence, the first term, and then I define it recursively, meaning the nth term is based off of the n minus first term, the term before it. And using the recursive formula, generate the entire sequence. As far as it goes, well, since I know the first term, if I wanted to list these out, the second term, by definition, A sub 2, would be 2 times A sub 2 minus 1 plus 1. That's A sub 1. A sub 1 is 4, so I plug that in here, and I get 2 times 4 plus 1, which is 9. And then A sub 2 is 9. To get A sub 3, do the exact same thing. A sub 3 equals 2 times A sub 3 minus 1 plus 1. A sub 3 minus 1 is A sub 2. A sub 2 is 9. So this becomes 2 times 9 plus 1, which is 19. And then we can keep on doing this. Essentially, you need to know at least one term, and once you know one term with the recursive formula, you can generate the entire sequence by just applying the rule to the previous term over and over and over and over again. Well, there are some other things we can do. Once we have the recursive form, well, let's see. One thing that will pop up is something that looks like this. Say 5 exclamation point or 7 exclamation point or something like that. If you haven't seen those before, those are called factorials. And as far as the definition goes, n factorial is n times n minus 1 times n minus 2 all the way down to 1. So basically, n is a positive integer. N factorial is the product of all the integers from n down to 1. So 5 factorial is 5 times 4 times 3 times 2 times 1, 120. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 5,040. And so on and so forth. We will be using these in our sequences, so you have to make sure you recognize that your calculator actually has a button that will generate them for you if you don't want to multiply them out. Look under the math probability command or some form of that based on what calculator you're using. One trick that we will need that might occasionally pop up, 0 factorial. Clearly, if the definition of a factorial is the product from n all the way down to 1, then 0 doesn't really make sense because, well, it's already past 1, so I can't count down to 1 from 0. I'm not going to go into the proof of it and all that, but just by definition, 0 factorial equals 1. So if that ever pops up, just remember 0 factorial equals 1. As far as it goes, for right now, that is a lot of the definitions that we need for sequences. We know what a sequence is, we know what its domain is, we know they can be finite or infinite, we know their functions, we can plot the points, see what's going on. Once you have sequences, you can define them by listing the terms out, a sub 1, a sub 2, blah blah blah, all the way down to a sub n. Or you can define them recursively, figure out the first term, or you're given the first term, and then have a sub n written in terms of a sub n minus 1 or something like that, and generate it term by term. There's also explicit forms, which, like I said, we are going to do more of in the next two sections of your book when we look at specific types of sequences in their explicit forms. And then we have these factorials. Make sure you can deal with them. The last thing is, well, once you have sequences, you also talk about what's called series. And essentially the idea is in math, if I have a sequence, we'll go back to the sequence I had before, 1, 4, 9, 16, 25, and so on. Once you have a sequence, a whole bunch of numbers, the next logical question mathematically is, what can I do to all those numbers? And one of the things we like to do is add them up. So a series is just the sum of a sequence where you add up all the terms, even though there's an infinite number of terms. The way we actually write it, we use this notation. It's called sigma notation. We'll say I equals 1 to 5 for the purposes of this, we'll use that one, I squared. And essentially the idea is, again, this is called sigma notation. This is a Greek capital sigma, which is why it's called sigma notation. In math, it just means sum, adding things, which is what series are. This I right here is called the index of summation. It can actually be different letters. A lot of people use N, you can use I, it doesn't matter. But essentially, this is the index of summation, and this is the lower limit of the summation, that's the upper limit. And how this works is, this index goes from 1 to 5, so you take this sum right here, and you replace I with 1 through 5 and add each of those values up. So since this is my sequence over here, if I is 1, I get 1 squared 1, plus if I is 2, I get 2 squared 4, then I get 3 squared 9, 4 squared 16, and 5 squared 25. We've gone from lower limit 1 to upper limit 5, so that's my series right there. Now add all the terms up. 1 plus 4 is 5, and 9 is 14, and 30, I think that's 55. And there we go. Ultimately, for right now, that is pretty much all we need, given some series. Say we have the summation I equals 2 to 5 of 2i plus 3. Keep in mind here, my index did not start with 1. It doesn't have to. It can start with anything, and it can go up to anything. This is still finite. Now, do the same thing. Plug in I equal to 2, and keep on plugging in until you get to I equals 5. If I plug in 2, 2 times 2 is 4 plus 3, 7. Plug in 3, 2 times 3 is 6 plus 3, 9. Plug in 4, 2 times 4 is 8 plus 3, 11. Plug in 5, 2 times 5 is 10 plus 3, 13. Now just add those up. 7 and 9 is 16, 16 and 13 is 29, and 11, I think that's 40 if my quick math is correct. And that's my sum right there. The ultimate goal is to take some series and say I equals 1 to infinity. Add up an infinite series. And we will actually have tricks to do that we will learn in the next few sections of your book. For right now, for you guys to ponder, if I say use my series I squared, do I square all the numbers? Obviously that answer is going to be infinity, because I'm just adding bigger and bigger and bigger and bigger numbers. The question becomes, what if I have a series like I equals 1 to infinity of 1 over 2 to the I? I will say right now at the outset as we do this, I use n's a lot, not i's, so I might accidentally go back and forth between n and I. Just be aware of that. But here, what if I have that series right there? What would it add up to? We are going to mess around with that and actually, probably by the end of this week, have an answer to it. But for right now, just think about it. And we'll maybe come up with a few tricks to help us get an idea of what's going on.